Hi guys. We're here to talk a little bit about momentum today. Here, I'm going to shrink my screen real quick, just so we'll just move it over a little bit. There we go. And essentially, if you remember from last time, we talked about how momentum is conserved, right? That whatever the momentum is before the system, it has to equal the momentum after the system, or the momentum before a collision has to equal momentum after a collision. And that is sort of what we are going to do today. The math we are going to do as well will involve this. This is a little intense as far as some of the math goes. I don't know if the word intense is right, but it's just you're going to need practice at it. And I would say this is probably the most math we're going to do. It doesn't mean you can't be successful at it, even if we're going to break it down. We're going to do it by step, and you guys just will see the process is very, very similar. In case you forgot, we're going to talk about these two different types of collisions as well. One is elastic, which is objects that don't combine after they collide, and then inelastic, which is objects that do combine after they collide. They lose kinetic energy as well. These ones do not. This is what we need. So here's the math. Here's what we're going to do. This is really, really important, though. You got to remember that momentum before the collision has to equal momentum after. So that's sort of going to define all of these problems. We always are going to use this law. This is how we are able to establish this. It's momentum before equals momentum after. That looks really, really easy, right? Here's an elastic example is like two objects that are hitting each other. The example we do here are billiard balls that are going to collide. And this is the equation. I would pause your video now, record this, is that the mass 1 and velocity 1 initially plus the mass 2 and the velocity 2 initially has to equal the mass 1 and the velocity 1 final plus mass 2, velocity 2 final. So what we're really saying is, remember, momentum equals P equals mv. So it's the momentum of object 1 plus the momentum of the object 2 before they collide has to equal what they finish, which is momentum 1 plus momentum 2 after the collision. Inelastic, remember, these are the ones that stick together, is very, very similar equation, but so it starts the same, right? It's the M1 V1 initial plus M2 V2 initial. But the difference here is that you're combining the masses at the end. So that's why we have this M1 plus M. And then since it's only one object, we're looking at it as only one velocity. So that's the difference between the two. You're always just going to look back. We'll talk about our steps here, so that way it's less confusing than that. All right. So here's our first practice problem. So it's a billiard ball that sits at rest on the table while the cue ball, which has the mass of 1.5, is shot at it with a velocity of 15 meters per second. After the collision, the cue ball continues to move forward with a velocity of 2 meters per second. What is the velocity of the billiard ball after? Here. So first step you're going to do is pick object 1 and 2. You got to identify which object you want to make object 1 and which object you want to make object 2. I am always just going to do it in the way that it is presented. So as soon as I see the first one, so it says a billiard ball, boom, object 1. Then I see the cue ball, object 2. That is your example there. That's how I will always do it. For these types of problems, guys. So what type of collision is this? So you now have to identify what type of collision with it. So same exact problem. We know these two billiard balls are colliding. So do they stick together, though? That's the big question, right? You need to ask yourself, do these objects stick together? And the answer is no, right? Think about what a billiard ball would do is you got one here, they hit each other, they're going to move. So they're not sticking together. Therefore, we know, boom, elastic. So right away, you would go and you're going to write down your elastic equation. That's what you need to do next. So this is our next step, is write down the equation that you need. Remember, you can always just look back, guys. Look back if you forget, or, look at your notes. You need to have these written somewhere, and that way they're easily accessible. So here we're going to write down our equation. The next step, I'm going to move this so that way we don't see that little perfect. You got to label every single thing here. So you need to identify everything you need to do. And this is why it's going to help. One, we've already established the equation. So you're just sort of plugging in each step of the way of what we've already identified. So we've already talked about it. Billiard ball 1 is what we call object 1. The cue ball is object 2. So M1 is the billiard ball. It's 2. Boom. Check. Got that one down. Now we will go to its object is at rest. So the velocity is 0 meters per second. So we're already here there for those 2 parts. Then we go to the cue ball, which is 1.5. And then we have a velocity of 15 meters per second. So we have this number as well. That is everything on the left side of the equation already done, completed. Now, we're looking for the cue ball after. So we write down what we still know. The masses has not changed, right? It's not like the mass changes after the hit. So boom, we write M2, but we don't know what this velocity of the billiard ball is. We do not know it. So that's where we're going to make our little question mark. Then we just plug in our next part, which is M2. We have that 1.5. That does not change because it's the same object before or after the collision. And it says right here, the final velocity of is 2 meters per second. So those are every single thing you need to write down. I know that seems like a little bit, but you're going to need to take this step by step if we're going to want to remember. Now, once it's all in, once you got all this part, you're just literally plugging in your numbers. This is once it's become easy. That step 4 is obviously the part that tends to be the one that trips people up. If you get to there, normally we're pretty good sailing from that. Now we're just plugging everything in. So we have 2 and a 0. We have a 1.5 and a 15. We have 2. I'm going to just write X, guys, for right now. And then we're going to add these 2 numbers together. So boom, we got all of these numbers multiplied together. I'm going to add the left side. So we have 24.5 and then the 2X plus 3. And then it's just a little algebra. We're going to subtract that 3 from the right side, move that over. We get 21.5 and then divide each side by 2. And that way I get X equals V, and this is definitely supposed to be 11.75, not 25, guys. That was my bad there. So that is our equation for the first one. Now, let's look at the second one. It is similar in concept, but different in execution. So we're looking at Naz, and it says that he has a mass of 80 kilograms. It's moving 11 meters per second to the right. When he tackles Williams around running back, who's moving at him. So that would be to the left. So that's why you're going to see this -3. Remember, rights and lefts. We're back to that, guys. Assume they stick together after the collision. So it's the same steps, right? 1, pick object 1, which I'm making Naz, and then object 2 is the Williamstown running back. That is what I will do because that is the order they were presented to me. Boom. Next step. What type of collision is this? And my answer is, do they stick together? And I highlighted it here because I think it's right. Do they stick together? Yes, they stick together. It says they stick together. So we are going to make it inelastic this time. So difference here, you need a new equation, right? Different problem. It is similar, but at the end, the masses are going to combine because they are sticking together. All right, confusing part. Well, maybe, I guess. This is the hardest part. This is the part you need to make sure you're taking at least the most time with, guys. And it is Naz, we have equals 80. That's mass 1. We have velocity 1 here. And this is all initial. This is before they collide. And then we have the Williamstown running back, which we call M2. And then we have it 90. And then a velocity of -3 meters per second towards him. So they're going towards each other. At the end, they're going to combine. So we need to make sure we do that same thing. So we need M1, which does not change, M2, which does not change. The velocity final, we don't know. We know that will probably change because it has to. So therefore, that's the one we are going to write down that we do not know. And now we're just plugging in our numbers again. This is the same process. Once you get to here, it should be plug away, right? So we got 80 times 11 plus 90 times -3. Equals 80 plus 90x. Boom, we do a little math. 880 minus the 270 equals 170x. 610 equals 170x. And then we just divide 3.59 meters per second. Boom, boom, boom. All right. We got one more type of problem, and it is we call them explosion types. They're essentially the same thing. Honestly, these will probably end up being your favorite type because I think they are the easiest mathematically, but they look a little different. So we're talking about a gun that's in space and it is shot. Obviously, we know because of Newton's third law, if we have one object going one way, there has to be a little kickback of the gun the other way. So we know that the gun moved back with 1 meter per second. So how fast must the bullet be traveling? So the question I guess you really need to ask is, what's the initial momentum of the bullet and the gun before they were fired, right? And is there any external forces acting on the system? Both of these answers are similar. So is there any external forces? No, it's in space. That makes it really, really easy. And then a loaded gun here is important because we see, is there a gun that's fired in space? Which way is the bullet going? So how much momentum does this have beforehand? And remember, objects that don't move don't have any momentum, right? It even says both the bullet and the gun are at 0 meters per second, which honestly, you'll see will make this problem really, really easy. So it sort of looks like this. Bullet's going one way, gun is going the other. So let's do the same process, guys. The exact same process that you've been doing. Step 1, gun and object 1, bullet and object 2, right? Because that's the way I like to do it, right? Which is the gun is the first one. Therefore, I'm going to make that object 1. That's just sort of how I am. So what type of collision is this? After they're shot, do they stick together? And the answer is no, right? They're two separate objects. Therefore, must be elastic. That is not different. Just like step 3 would be for the billiard ball, we write down the same equation, right? It's still an elastic collision, even though it is 0, right? So boom, 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 boom. We write down all of those stats. And here you're just going to label everything, right? So you read the problem again one more time. We know object 1 has a mass of 5. The velocity is 0. We already talked about that. The bullet has a very small mass of 0.01 kilograms, and then its velocity also is 0. So we'll see that whole left side is going to be 0, guys, right? Because it's 0 times 0. Then we have 5 and 1, and then we have this 0.01, and then we don't know the velocity of the bullet. That is what we are looking for here. So boom, boom, boom. Now we're just plugging in our numbers once you label everything. So we have 0 times 5 is 0 times 0.01, and then a 5 times 1, and then the 0.01 times the x. I have 0 plus 0, and then the 5 plus the 0.01x. And now you're just combining your terms, right? What is nice is you'll see, hey, 0, 0. What will be always sort of true is you're always going to have one velocity be positive, one velocity be negative. And you guys can think about it. If one object's going to the left, that has to be negative. This one has to be positive. If the roles were reversed, one object would be positive, the other one would be negative. Or you could just think about it in the way that we say, hey, if we add these two numbers together, right, they have to equal 0. So if one of them's positive, the other one has to be negative, or you can't get it to 0. Same thing is always going to be. So one will be positive, one will be negative. But you just do the math out. You could just move this 5 over to the left side. We get a -5, and then you divide it by 0.01, and it turns out that velocity 2 equals 500 meters per second. That is also supposed to be a VF, right? Like it's definitely not the initial there. So that is everything, guys. I know it is a little hard. We will continue to practice this later.